Swayam Prabha. Digital India. Educated India.
In this lecture, we will continue our discussion on conservation of momentum and energy. So, these are the concepts. We will look at momentum conservation in integral and differential form, relevance of energy equation for high speed compressible flows, and energy conservation in integral and differential form. These are the key points for the lecture. As you recall, last time we were discussing about shear stress and normal stress. So, I am just recapitulating one of the components. So, in the xy plane, you would see tau xy and tau yx equal to each other given by this expression. Giving an example of normal stress, this is how it comes, where lambda is bulk viscosity coefficient, and George Stokes, a very famous scientist, he made a hypothesis that lambda is minus 2/3 mu, the viscosity coefficient. So, according to that, we say that this coefficient will be minus 2/3 mu times divergence V. Like sigma x x, you can define sigma y y and sigma z z. Remember that when it comes to shear stress, there has to be a combined presence of the velocity gradients as well as the viscosity coefficient. So, this part comes from the flow field, this is a fluid property. So, the combined action of the two leads to viscous shear stresses. These are the viscous normal stresses. Again, as you can understand, the presence of these gradients, the divergence of the velocity field will contribute to the presence of a normal stress. So, keeping these in mind, we can define the viscous force coming out as an outcome of these stresses in this form, without bothering too much about the actual representation of these components, which we will see in a later part of the course. You can say that this is how one can represent the viscous force in totality. So, now what do we have? We have a representation of the total force which can act on the fluid in the control volume. So, that is due to the combined effect of different forces, both body force and the surface force. So, if you just concentrate on the surface force due to pressure, then only the effect of this term will matter. Now, time rate of change of momentum of the fluid as it sweeps the control volume is this term in Newton's law, and that would be due to time rate of change of momentum due to unsteady fluctuations in flow properties, which would alter the content of momentum within the control volume. And the other comes from the net flow of momentum out of the control volume across the control surface. So, looking at the different terms that we just wrote, let us name these terms. Let us call this as A and this as B. So, the A part can be written as this, the time rate of change due to unsteady flow fluctuations, and the B part would be the combined effect of mass, flow rate and the velocity. This is basically m dot, and then you would actually have to integrate the contribution over the entire surface of the control volume. Again, the positive contributions will mean outflow of momentum, negative contributions would mean inflow of momentum. This is how we assess it. So, putting all the terms together, that means the A B terms on one side and the force terms on the other, what do we get? This would be tensity and we are having all the force terms on the right hand side. Once we do that, we will apply the gradient theorem to obtain the momentum conservation at a point in the flow, because this expression is basically the integral form of momentum equation or momentum conservation equation. So, we will now like to take it to the differential form, which would be valid at a point. How do we do it? We apply the gradient theorem in order to convert the pressure term from a surface integral to a volume integral. Then, since we are using a fixed control volume, we can convert the time derivative term to a form like this, where we put the time derivative expression inside the integral, and then we can make one more simplification, for which we have to write down the components of the velocity vector first. So, these are the components of the velocity vector. So, when you look at the momentum flux term, what do you have? You have an integration of this. So, if you take the u component or the x component of this, what is the outcome of that? It will give you integral of rho v dot ds times u, that means only the x component coming from v. Similarly, the y component will have a v here, w here and so on. So, if you do that, then there is a simplification in the sense that applying divergence theorem, you have to integrate this as a surface integral. So, you convert it into a volume integral. So, this is done through application of divergence theorem. Similarly, as you can understand, in the y and z components, you will be working out divergence of, let us say, rho v capital V or divergence of rho w capital V and so on. So, finally, if you collect all the terms, what do you have? You have when it comes to the viscous term, we will just use a particular nomenclature. I am underlining the term because the viscous term, each component of it we had represented in the form of a component of the total force. Now, this force comes under the volume integral. So, actually how we interpret it is the x component of the viscous force is now being represented in this form, in an appropriate form which goes into the volume integral. Now, as you can understand, if it goes to 0, then this entire expression has to be equal to 0. So, that gives the x component of the momentum equation in differential form. Similarly, you can write y components and z components. I am just writing it in a more simplified manner by considering only the pressure gradient term and neglecting the body force term. So, you have the time dependent term, then the divergence term and the pressure gradient term only in the momentum equations because of the simplification I mentioned. Further, if it is a steady flow, as you can understand, this will go to 0 and so on. Now, if you retain all these terms, then you get Navier-Stokes equation. If you remove the viscous terms, you get Euler equation. If you neglect the body force terms, that you can for both Navier-Stokes as well as Euler, if you are handling light fluids like gases. So, with this we complete our discussion on momentum equation. We will now go to energy equation. Before we derive energy equation, we have to address a very important conceptual point, that is, energy equation is particularly relevant for high speed flows, especially of air and different gases. And the primary reason behind this is that when we talk about high speed flows, we are talking about very high kinetic energy of the gas. So, per unit mass you can say that V square by 2 term, that becomes very relevant, it becomes very large. and then it can have a very substantial influence on other flow properties, because it is a large term in the conservation equations. And we know that the energy and entropy issues of a gas flow will be handled through thermodynamics concepts, and thereby we invoke the first law of thermodynamics, which involves energy conservation, into the picture when we are handling such high speed flows. In general, high speed flows are also compressible flows. So, keeping these concepts in mind, we would say that for compressible gas flows, energy equation is one of the most relevant equations. Keep in mind that in compressible flows, we will talk about large density changes, and then a very important concept comes into the picture, compressibility. So, you can define it by saying that it is a fractional change in volume of a fluid element per unit change in pressure. And if you define the compressibility term as tau, then we could show that there is a relation existing between density change and pressure change in a compressible fluid flow. So, this relation basically sums that up, where compressibility plays a very vital role. It basically says that in a fluid flow, the fluid elements undergo change in pressure, and if those pressures are non-trivial, then there are also non-trivial density changes, provided that the compressibility of the fluid is not extremely small. Now, liquids have very small taus, while gases have large values of taus, and therefore, even for moderate changes in pressure, a fairly large value of tau would produce significant changes or non-trivial changes in density. So, that is the concept that we have to deal with in compressible flows. Now, usually what we see is that in low speed flows, the pressure changes are not all that high. So, even though compressibility of gases is significant, the density changes are not very significant. However, that is not the case when the flow velocities are large. Now, we were talking about the first law of thermodynamics being invoked into the picture. So, as we do that, we would notice that apart from the variables that we were handling till now, we would have to additionally handle two more variables. One is the internal energy per unit mass represented as E, and the temperature of the gas, capital T. We begin our discussion by defining a thermodynamic system along with its surroundings, and we know from our basic knowledge of thermodynamics that the system has an working fluid, comprises of gases or a single gas with its molecules moving around in a random motion, and it has a fixed mass. And how it can exchange energy or rather exchange heat and work with the surroundings could be represented like this, that different kinds of heat and work exchanges would lead to change in internal energy of the gas. So, we already said that internal energy per unit mass is given by small e. So, that is by virtue of the continuous motion of the atoms and molecules which comprise the gas. So, if you exchange heat and work with the surroundings, then there is a change in the internal energy. These are inexact differentials because they are path functions, while this is an exact differential because it is a state function. Now, keeping all these things in mind, when we apply this first law that we are defining for a system to the flowing fluid through a fixed control volume, then what is the implication? We say that rate of change of energy of fluid as it flows through the control volume is equal to rate of heat added inside control volume from surroundings and rate of work done on fluid inside control volume. Of course, there are different means by which you could do the heat transfer and the work. So, the heat addition or the heat exchange in an additive or subtractive sense could be due to different reasons. One is, say, chemical reactions occurring within the control volume. Typically, if you are burning fuel in an airstream, like it happens in the combustor of a jet engine, or there could be other reasons. There could be heat transfer through conduction or radiation, let us say mass diffusion, and at high speeds there could be a lot of heat generation due to viscous dissipation. There are different means by which heat could be generated. So, in totality one can say that it could be represented like this. So, it is per unit mass that we are representing the Q dot as a rate. Similarly, the work done again can be due to different means. It could be the pressure acting on the control surface or the body forces or the shear stresses that we discussed about. So, pressure, body force, shear stresses or other interactions like shaft work etc. are also possible. We are just going to talk about the effect of pressure. So, when it comes to pressure, this is the force it generates, and then when it comes to using it in this equation, the basic idea is that we are talking about a force which is acting over a certain fluid causing its displacement. So, if it was just work done, then one would have done a dot product between the force and the displacement that it creates. So, let this be the displacement, then that dot product would have given you the work, but here it is a time rate that is involved. So, it is essentially a dr dt which gives you velocity. Therefore, you see the force due to pressure dotted with a velocity. You must have noticed that here when we look at this rate equation, it essentially boils down to time rate of heat or time rate of work etc., which essentially means we are dealing with power, not energy. So, This is a little bit about the heat and work exchanges which are possible. Now, as far as the fluid in the control volume is concerned, unlike the system, the thermodynamic system, where the fluid was not having any bulk movement, it was just having the molecular motions, here the fluid also has bulk movement. So, due to molecular motion it had internal energy, due to the bulk motion now it has kinetic energy. Additionally, if it was a heavy fluid, it would also have potential energy, but because we are handling gases, predominantly air, we are not going to talk about potential energy. So, we just confine our discussion to internal energy and kinetic energy. So, when we put those together, we are going to write two terms which show the internal energy content within the control volume, how it changes with time, and its internal energy and kinetic energy flux across the control volume surface. So, these are the two effects. So, this is the time rate of change of the content and this is the flux. So, now putting everything together into the equation, we have these two terms. We will slightly rewrite this second term like this, so that we can take the dot product there onto the right hand side, and then we can indicate the heat and the energy exchanges. So, this is essentially the integral form of the energy equation. Now, we have already done two exercises with continuity equation and momentum equation, where you saw how we suitably converted it into a form where we can apply it to a point in the fluid, so that we can get the differential form of the equation. So, using that same concept, we can convert this equation to a differential form, and there you will find that it can be written like this. You can try deriving this as a homework. Now, as you can understand, if the flow is steady, then you can drop this term. If the flow is adiabatic, that means there is no heat transfer, then this term can also be dropped. So, these are simplifications which one can think about for certain cases. If you do that, then the integral form will boil down to a simpler form, like you will be just left with this part on the left hand side and this part on the right hand side. That would be the integral equation. What will be the this would be the differential equation. What would be the corresponding integral equation? It would look like this. That is, we did two simplifications. One is that we considered steady flow, the other is that we considered that there is no heat exchange, that means it is an adiabatic flow. If we do that, then these are the two forms. So, this is the integral form, the other is the differential form. Now, what have we derived? We have derived three equations till now. One is the continuity equation, the other is the momentum equation, and the third is energy equation. And we hope that we will be able to handle compressible flows using these conservation equations. But incidentally, we are now having 4 unknowns to solve in these equations. It is pressure, density, velocity and internal energy. That is a new variable which has come into the picture. That means we are falling short by one equation. So, in order to bridge the gap, we will bring in another equation which will help us to define internal energy. So, we bring in what is called as the thermodynamic state relation for E, and that is what? For a calorically perfect gas, that means perfect gas for which its specific heat at constant volume or specific heat at constant pressure remain constants irrespective of the temperature. That means, this value remains constant for a calorically perfect gas. We have now been able to define E in terms of this constant and temperature, which means a new variable has come in, temperature. How do we solve the problem now? Because we are still short by one equation now, because there are now 5 variables and we have 4 equations. That means, these 3 and the thermodynamic state relation, which makes 4 equations, but 5 unknowns. Now, we invoked the perfect gas equation of state to bridge the gap, which gives us a relation between pressure, density and temperature. We have this R as what is called a specific gas constant, and that is represented in terms of the universal gas constant, let us say R over bar, by the molecular weight of the gas, where there is a value for the universal gas constant, which is 8314 joules per kg Kelvin. So, that is how now we have 5 equations and 5 unknowns. So, the equations are continuity, momentum, energy conservation, then the thermodynamic state relation and equation of state for the perfect gas, and the 5 unknowns are pressure, density, velocity, internal energy and temperature. Therefore, now these 5 variables can be solved if we solve these 5 equations. So, with this we will end our discussion on momentum equation and energy equation, which we discussed in this lecture. So, we will conclude this lecture by saying that we discussed about the momentum conservation equation in integral and differential form, where various forces acting on the fluid were equated with its time rate of change of momentum. And then relevance of energy equation for high speed compressible flows was first discussed. Then the first law of thermodynamics was applied to a control volume to obtain the energy conservation equation in integral form. Then we extended it to the differential form, which applies at a point in the fluid field. To solve the unknowns in compressible flows, 2 more equations, namely the thermodynamic state relation for internal energy and perfect gas equation of state, were introduced in order to solve the necessary variables. So, with this we end this lecture. Thank you.